is found in the 2p orbital of the hydrogen atom. So here we have the diagram of the 2s orbital and the 2p orbital. So what exactly is the 2s orbital? So the 2s orbital has a principal quantum number of n equals 2. It has an orbital quantum number of L equals 0, and our magnetic quantum number ML is equal to 0. Now, in contrast, the 2p orbital basically has three different orientations. We have one along the x-axis, one along the y-axis, and one along the z-axis. So the one along the x-axis has a magnetic quantum number of ML equals -1. Now, our y-axis oriented orbital has a magnetic quantum number of ML equals 0, and the z1 has an ML of +1. Now, for each one of these orbitals, the principal quantum number as well as the orbital quantum number is exactly the same. The difference lies in the magnetic quantum number. Now, the question that we want to examine is the following. Suppose our electron is found in either one of these orbitals. Let's suppose it's found in the 2pz orbital. The question is, if we follow these selection rules, can our electron actually jump from our 2pz orbital to the 2s orbital? So from the selection rules, we see that the electron can in fact jump from any one of these 2p orbitals to the 2s orbital. And the reason is, if we look at the change in the orbital quantum number, we go from L equals 1 to L equals 0. And this corresponds to a delta L of -1. So that means regardless of whether our electron is found in the 2py, the 2pz, or the 2px, that electron can in fact transition from either one of these orbitals to the 2s orbitals and release a photon of light. Now, on the contrary, let's suppose our electron wants to transition from the 2pz to the 2py, or from the 2py to the 2px. Can that actually take place? So notice that the electron cannot actually jump between one of these three 2p orbitals, and that's because in such a case, the change in the orbital quantum number, delta L, will be equal to 0, and delta L cannot actually take place. So basically, these transitions are known as the forbidden transitions, and this transition, as discussed earlier, is known as the allowed transition. Now, once again, even though this transition is known as the forbidden transition, that basically means it can actually still take place, but it is very unlikely. There is a very small probability that such a transition will actually take place, versus in this case, where there is a very high probability that such a transition can actually take place. So once again, these rules, known as the selection rules, are in place and are used in quantum mechanics to determine which electron transitions are the probable ones and which ones are the improbable ones. Every single electron has an intrinsic property known as the electron spin. Creates something called the electron. Generally speaking, how a magnetic dipole moment is formed. So recall that a current loop forms a magnetic dipole moment that is given by this equation. So basically, we have a conducting loop of wire that carries a positive electric current, let's suppose in a counterclockwise direction. And as it travels, it will basically form a magnetic dipole moment that is given by mu that points upward perpendicular with respect to the area that our loop of wire encloses. Now, if the area is given magnitude of the magnetic dipole moment mu is given by taking the product of I, the current, and A, the area. So this gives us the magnitude of the magnetic dipole moment formed by the current loop. Now, what about the electron magnetic dipole moment? Well, if we treat our electron as if it was a particle, then we see that the electron actually creates its own electric current that loops or orbits the nucleus of the atom. So let's suppose the nucleus of the atom is at the center of this loop. So basically we have the electron, which now moves not in the counterclockwise but in the clockwise direction, and as it moves, because it has a negative electric charge and it moves with a very high velocity, it basically creates a continuous negative electric current. And that's exactly why we have to reverse directions. So if we have this negative electric current that is created by the charge on that moving electron, if we have this negative electric current, it will create a magnetic dipole moment that also points upward perpendicular with respect to the area. Now, in our discussion on classical mechanics and the electrons orbit around the nucleus, we were able to show that if we take this equation, we can actually obtain equation 1, where equation 1 gives us the magnetic dipole moment of the electron as it orbits the nucleus of the atom. So mu is equal to E multiplied by V multiplied by R divided by 2, where R is the radius of the orbit, V is the velocity of that electron in orbit, and E is the charge on that electron given by negative 1.6 times 10 to negative 19 coulombs. Now, anytime we have a particle with a mass m that is undergoing rotational or angular motion, that object with mass m and velocity v and radius r creates an angular momentum that is given by this equation. So we take the product of the mass m, the velocity v, and the radius of orbit r, and we get the angular momentum that is created by that electron's spin. Now, if we rearrange this equation and solve for the velocity, we see that the velocity of the electron as it spins around is equal to L divided by m times r. Now, let's call this equation 2. If we take equation 2 and plug it into equation 1 by basically replacing the velocity with L divided by m times r, we get this result, and notice the r's appear on top and bottom. We can cancel the r's, and we get that the magnetic dipole moment that is created by the electron is equal to E divided by 2 times m multiplied by L, the angular momentum. So let's call this equation 3. Now, this gives us the magnitude of the magnetic dipole moment. What about the direction? Well, the direction of the magnetic dipole moment of the electron lies in the same axis, lies along the same axis as the direction of the angular momentum. But because the electron has a negative charge and the charge on this current is opposite to this charge, which is positive, that means they point along the same axis but in the opposite direction. So if L points up, the mu, the magnetic dipole moment, points downward. So once again, the angular momentum L of the electron points along the same axis as the magnetic dipole moment mu of the electron, but in the opposite direction. So that means we have to put a negative in front of this term. And we see that the magnetic dipole moment of the electron is equal to negative E divided by 2m multiplied by L, where m is the mass of that electron. So basically, this gives us the electron's magnetic dipole moment created by that spin in terms of the angular momentum of that electron. Now, we can also also express the electron's magnetic dipole moment in terms of the orbital quantum number. Now, in our discussion on quantum numbers and the quantum mechanical theory of the atom, we were able to show, or actually we simply said, that the square of the angular momentum L is equal to h bar squared multiplied by L plus 1, where h bar is a constant and L is the orbital quantum number. So basically, if we take the square root of both sides, we isolate L, and we see that L is equal to h bar multiplied by the square root of L multiplied by L plus 1, where L, once again, is the orbital quantum number. Now, if we take this L in this equation and replace L with this, we get the following equation. So this equation gives us the electron's magnetic dipole moment in terms of the orbital quantum number. So mu is equal to negative E, the charge on an electron, multiplied by h bar divided by 2m, where m is the mass, multiplied by the square root of L, multiplied by L plus 1. So this equation gives us the magnetic dipole moment of the electron moving about the nucleus of that atom. Now, what happens if we take our electron that is spinning, so the electron has a spin, that creates a magnetic dipole moment, and now we take the electron and we place it inside an external magnetic field. So let's suppose the direction of the electron's magnetic dipole moment points along the following axis, and let's suppose we place it inside a magnetic field B that points upward as shown. As soon as we turn this field on, basically this magnetic field B will exert a torque on this electron's magnetic